What's up everyone, Patrick here, welcome back. Moving on to the next question, dealing with quadratics. This is more so a communication type of question, so we have to comment on the number of x-intercepts between y equals x squared plus 9 and y equals x squared minus 9. So notice these are similar quadratics, only difference is the sign that is in between the expressions. Now I'm going to show this both algebraically and then also graphically how both of these graphs relate to each other. So let's start off with y equals x squared plus 9. Now, how do we find x-intercepts algebraically? Well, we plug in 0 for y. And this actually, from here, what we do is usually try to factor it. This is actually not going to factor. This is, if you notice, x squared minus 9 is a difference of squares, but there's a plus over here. So this is not going to factor, and you can actually confirm that as well. So if we rewrite this as x squared plus 0x to bring in that b value plus 9, so a value is 1, the b value is 0, the c value is 9, the ac value is 1 times 9, which is 9. So we got to find two numbers that multiply to positive 9 and then add up to that b value of 0. There's no two numbers that are going to satisfy this over here. Okay, so this actually won't factor. Now, another way you could try to do this is directly solve for the x, because there's no bx term over here. There's no other x variable to worry about. So you could bring the 9 over, and you'd end up with x squared equaling negative 9. When you try to square root both sides over here, this would be undefined. You can't square root a negative number. Okay, so y equals x squared plus 9, it actually has no x-intercepts. And I'm going to show graphically also why that is in a second. Let's just show graphically how many x-intercepts y equals x squared minus 9 has. So if we plug in 0 for y, two different ways to do it. The less proper ways to directly solve for it, though you can directly solve for it here pretty easily, because again, you don't have to worry about that bx term, right? So there's only one x value to isolate for. So it's not too bad to try to do that. So we bring the 9 over, we'd end up with x squared equaling positive 9 this time, and then when we square root both sides, we get x equals plus or minus 3. So there's actually two x-intercepts in this case. Both of these x values over here would give you a y value of 0. Now the proper way to show this is to actually factor this. Notice how it's a difference of squares. X minus 3, x plus 3, like that. And so when does x minus 3 equal 0? When does x plus 3 equal 0? Happens when x is 3. This happens when x is negative 3. Okay? So there's two x-intercepts for this quadratic right here. It's x equals plus or minus 3. So we showed algebraically how it works. Now graphically, if you remember, if you have a quadratic that is in the format y equals ax squared plus c, again that bx term is not there, the b value is 0. I've mentioned this countless times before in previous videos. If you have a quadratic like this, the vertex of it is always going to be 0 and the c value. So for example, if you got like y equals negative 3x squared plus 5, the vertex of this is going to be 0 and that c value of 5. If you got y equals 4x squared minus 1, okay, over here, the vertex is going to be 0 and negative 1. That's c value right there. So from here, you could tell the vertex is going to be 0 and negative 9. Okay, with this property here, the vertex is going to be 0 and positive 9, like this. Another way you could tell that it's going to be 0 and c, the vertex, is this is also actually vertex form, because we could rewrite this as x plus 0 squared plus c. So notice that this here is the same as this. This is vertex form. Again, that vertex would be 0 and c. All right, so I've mentioned this before. So the vertex for both of these is going to be different. This one's going to be 0 and positive 9. This one's going to be 0 and negative 9. Now watch what happens when we plot these vertices on the graph. 0 and 9 is going to be here. And notice that this quadratic, it's opening up because we have a positive a value, a positive 1. So it looks like this. And so notice that this quadratic, it's never passing that x-axis. Hence, it has no x-intercepts. Versus this quadratic here, if we plot that vertex 0, -9, which is down here, well, notice that this quadratic is also opening up because we have an a value of positive 1. So if it opens up, notice if the vertex is here, it has to pass the x-axis twice. And more specifically, it's going to pass it at an x value of positive 3, or a coordinate of positive 3 and 0, and this one's going to be -3 and 0. Right, so just a couple of different ways to show this. Basically, the short answer, comment on the number of x-intercepts between these two quadratics. This one has no x-intercepts. This quadratic has